Algebra 2, Chapter 5, Section 6, Systems of Linear Equations. A system of linear equations, or really just a system of equations in general, is a set of equations that must all be true at the same time. This is true of any system of equations. It doesn't have to be a linear system. A system of equations is indicated using a large opening brace like this to group the system of equations into one set. A solution to a system of equations is a set of values for the variables. So in this case there's two variables, x equals law, y equals foo, that makes all of the equations true at the same time. So one solution has a value for each variables, and each equation must be true for those values of the variables in order for it to be a solution. And a system of equations needn't just have two equations. It could have 3 or 4 or 75. There's no limit to how many you could have. There are several ways that we will use to solve a system of equations. The first is substitution. In substitution, we solve one equation for one variable. So going back to this example, we could solve this equation for x, then substitute what we find into the other equation. So imagine we would have x equals 11 minus 2y. Substitute that into the second equation. This creates an equation with one variable. Solve for the variable, get the solution for y, and then back substitute what we got to find the value of the other variables. Another method which can work out really well in linear equation systems is elimination. With elimination, our goal is to manipulate the equations we have in our system so that when we add or subtract those equations, all but one variable is eliminated, which is why it's called elimination. That will help us to quickly find that value of that variable. Then we back substitute like we did in substitution to find the answer. And a third method is graphing. We can simply graph the equations and find their intersections, and the points at which they intersect are the solutions to the system. So let's practice. First, let's solve using substitution. So the first step was take one of the equations, doesn't matter which one, solve for one of the variables, doesn't matter which variable. Let's solve for y. Okay, now substitute what we have here for y. So plug what we have for y into the second equation. That gives us an equation with only x in it. Now we can solve for x. 2x minus 3x is negative x. 11 minus 14 is minus 3. So x has to be 3. That is, no, we're not done. Remember, we have to get values for all the variables. So we back substitute. We take either equation and plug in 3 for x and solve for y. So we have y is 14 minus 9, which is 5. So a solution to this system is x equals 3, y equals 5. Now we can check this by taking each equation and verifying that we have a true statement. 3 times 3 plus 5 equals 14. 3 times 3 is 9. 9 plus 5 is 14. Check. 2 times 3 plus 5 equals 11. 2 times 3 is 6. 6 plus 5 is 11. Check. This is a solution. Since there are two linear equations, we know that they would be a shape of a line. And remember, there's only 3 cases still for a linear equation. So this is the only solution. Now let's solve the same system using elimination. Elimination, the goal is to manipulate the equations to where we can add or subtract them to get rid of a variable. Now in some cases we won't have to do any manipulation, and elimination is very trivial. This is one such case. If I just subtract the second equation from the first, I get 3x minus 2x is x, y minus y is 0, 14 minus 11 is 3, and I'm done with finding x. Okay, this is why elimination is so useful, is there are cases where it's very, very quick. So all of that work we did with substitution to get x equals 3, with elimination we're already done. X equals 3. Now we do the exact same step as we did previously to back substitute to find y. Now we can use either equation. Let's choose the second one this time. 2 times 3 plus y is 11. Y is 11 minus 2 times 3 is 6, which is 5. So x equals 3, y equals 5 is our solution. Let's do a different one with elimination to show that it's not always so trivial. So our goal here is to figure out a quick way to either add or subtract the equations to eliminate a variable. Not so simple to figure out a way for y, but here with x, if I just multiply this first equation by 2, I get 4x plus 14y is minus 6. If I write the second equation below the first equation, we can see now if I subtract the second equation from the first, I'll eliminate 4x. 4x minus 4x is 0. 14y minus negative 2y is 16y. Be careful with your double negatives. Minus 6 minus 10 is minus 16. So y must be negative 1. So we already have our y value. Now back substitute. 2x, y is negative 1. Minus 7 is minus 3. Adding 7, 2x must be 4. So x must be 2. So our solution is x is 2, y is minus 1. Now we can also solve by graphing. To solve by graphing, we might want to put our equations in to slope intercept form. Here they are in standard form. So we need to move the 3x over. Minus 3x plus 14. Y is minus 2x plus 11. We draw some axes. Label them x, y. First line has a y-intercept of 14, slope of negative 3. So it will fall. Say 10 is here, 5 is here. So if we fall 3, if the slope is negative 3, we're going to rise negative 3, which is fall 3, and run 1. So we're going to come to here, and this is 14 minus 3, 11, and 1. Then we'll fall another 3 to 8, and 2. We'll fall another 3 to 5. At 3, we'll fall another 3 to 2, and then we'll fall to negative 1, negative 4, so on. Our y-intercept was 14. So if we have everything drawn in a straight line, which we may not here, get right on our points. So for Second line, we have a y-intercept of 11 and a slope of negative 2. So we would fall 2, run 1, so that's 11, 9, 7, 5, 3, 1, negative 1, and if we draw our graph accurately on graph paper, we'll see, sure enough, 3 and 5. Remember, 3 and 5 was the answer to this. It's the same. These are the same equations. So that the graphs touch or cross at the point 3, 5, which is x, comma y. So the answer must be x is 3, y is 5. Now let's solve this equation, this set of equations anyway. Let's practice elimination again. So this one's a little tricky because we need to multiply both equations in order to get something that'll cancel. So if we multiply this equation by 3 and this one by 2, we'll end up making y the same. So 6 times 3 is 18. 3 times negative 2 is negative 6. 3 times 8 is 24. 2 times 9 is 18. 2 times minus 3 is negative 6. 2 times 6 is 12. So now if we subtract these equations, we get 18x minus 18x is 0. Minus 6y minus 6y is 0. 24 minus 12 is 12. We get 0 equals 12. This should remind us of something. Whenever we get a falsehood, then we have no solution. And if we were to graph these lines, we would see that they are in fact parallel. They don't cross. Let's solve this system of linear equations. We'll do this one with substitution. So let's solve x. Solve for x. X is 4 plus 2y. Put that in where we see x. We have 2 times 4 plus 2y minus 4y is 8. 8 plus 4y minus 4y is 8. 4y minus 4y is 0. 8 equals 8. Okay, this is something that's always true. So we have truth, and it's no matter what the input is. So we have infinitely many solutions. And the solutions are, this is the case of two lines that are on top of each other, same line. So the solutions would be all of the possible solutions to either equation, because they're the same equation, they're equivalent equations. So if we find any values of x and y that satisfy this equation, then those are solutions. There's infinitely many solutions, and they all lie on this line, x minus 2y equals 4. And last but not least, let's talk about a larger system of equations. What if we have 3 equations with 3 unknowns? Well, we can combine elimination and substitution to do these. We can do it all with elimination or all with substitution. Kind of as you do these problems, you get a hang of how to simplify them to where it's not as hard as it looks. Okay, so the goal is to eliminate one variable in each step. Okay, so we don't try to just get rid of x and y all in one step. What we want to do is use different equations to create equations with just 2 variables and then solve it like we did previously. So right away I see that this equation and this equation, if we add them, the 2y's will go away. So let's add equations 1 and 3. So we'll get x plus negative 3x is minus 2x. Minus 2y plus 2y is 0. 3z plus negative 2z is z. 7 plus negative 10 is negative 3. Okay, so we have an equation here with x and z. Okay. Now let's do the same thing to get rid of y in the second equation, but let's multiply this one by 2 first. So we would get 4x plus 2y plus 2z equals 8. And if we add the first equation and 2 times the second, so add first and twice second, we would get x plus 4x is 5x, minus 2y plus 2y is 0y, 3z plus 2z is 5z, 7 plus 8 is 15. Okay, now we have two equations, two unknowns. Let's now, instead of using elimination, now let's do substitution for this step. So if we solve this one for z, I get z is minus 3 minus 2x. Substitute that in for z over here. I have 5x plus 5 minus 3 minus 2x is 15. Doing the distribution, we have minus 15 minus 10x equals 15. Adding 15 to both sides, subtracting 10, we have minus 5x is 30. 5 minus 10 is minus 5. Minus 15, we add 15 both sides to get 30. So x is 30 divided by negative 5, which is negative 6. So we have the value for x. Now we can go back and find z by substituting in here. Z is minus 3 minus 2 times minus 6. Minus 2 times minus 6 is plus 12. Z must be 9. Now we can plug into any of the equations the values 9 and negative 6 to get y. Just pick the first one. So we have minus 6 for x, 9 for z, (3 times 9 is 27. Subtracting, subtract 27 from both sides, and we get negative 20. Add 6, we get negative 14. Divide by negative 2, and we get 7. So we have this solution. X is minus 6, y is 7, z is 9. So you can see how we can even combine elimination and substitution in one system, where the system is big, just depending on which way we think will be quicker in order to solve the system of equations.